Welcome! In this video I'll show you how to solve problem 7.13 as it appears in the third edition of Griffiths' Introduction to Quantum Mechanics. Now the problem states the following. It says, suppose you're given a quantum system whose Hamiltonian H0 admits just two eigenstates, psi A with energy EA and psi B with energy EB. They are orthogonal, normalized, and non-degenerate, and you may assume that EA is the smaller of the two. Now, we turn on a perturbation H' with the following matrix elements. So psi A, the expectation value of the perturbation in the state psi A and psi B is 0, and the off-diagonal terms are H. Find the exact eigenvalues of the perturbed Hamiltonian is part A. Part B asks us to estimate the energies of the perturbed system using second-order perturbation theory. C says estimate the ground state energy of the perturbed system using the variational principle with a trial function of the form psi is cosine phi psi A plus sine phi psi B, where phi is an adjustable parameter. And finally, D says compare your answers to A, B, and C. Why is the variational principle so accurate in this case? Okay, so let's begin with part A. So we want to find the exact eigenvalues of the perturbed Hamiltonian. So to do that, we need to take our matrix for the Hamiltonian, which is H, and we need to find its eigenvalues, right? And that will give us the allowed energies. So we need to, how do we find the eigenvalues of a matrix? Well, we have to take the determinant of the matrix minus the eigenvalues times the identity matrix and set this equal to 0. But the issue is that we don't really know what H is, at least not for now. So H, we know H is the sum of the unperturbed Hamiltonian H0 and the perturbed Hamiltonian H'. So how can we find these two, H0 and H'? Well, we can find them from the definitions that were given to us, because we know how they behave when they get acted on. So what do I mean by that? I mean that if we have, right, some bra multiplying our H0 matrix, which will be comprised of HAA, HAB, actually it should be H0, right, because this is H0, AA, H0, AB, H0, BA, and H0, BB. And when it is sandwiched with a ket as well, we are going to end up with a lot of these matrix elements, right? So H0 times in this sandwich, so bra, psi, H0, AA, ket, bra, and then the same for each one of the others. But we know that the result that we get here is going to be EA for when we get psi H0 AA psi, and we get EB when we have psi H0 BB psi, and everything else is 0. So for that reason, there is nothing in the off-diagonal terms, and the diagonal terms are simply EA and EB. So when we make this choice here, when we select these values for the off-diagonal values, you can see that this is indeed true. So this matrix, which is already diagonalized, which is very nice, this is the H matrix, the H0, sorry, matrix, not the entirety of H. We still need to find H'. So H' will be even simpler because we are given each one of its matrix elements, right? We have H', AA, H', BB, H', AB, H', BA, right? So for that reason, we simply have to take these values and plug them into a matrix. So if we have H', I'm just going to make this very clear. So it is H' AA, H' AB, H' BA, H' BB. And in case you are curious about the notation, this is a very common notation for matrix elements. It simply means the expectation value of psi a. So actually, let me do this in general. So if we have h prime I j, it means psi a, h prime psi j. Okay, that's all that it means. And of course, in this case, we know that the diagonal terms are 0 and the off diagonal terms are h. So now we can add these two together and we can find h. So h is simply the sum of these two matrices. So we get EAH, H, EB. So this is the matrix for which we now want to find the eigenvalues. So that way we will find the allowed energies. So we have to use exactly this formula right here. So let's do it, and we get EA minus lambda, the off diagonal terms suffer no change, and then EB minus lambda. And we have to take the determinant of this and set it equal to 0. So this will of course lead, now we know how to calculate a determinant for a 2 by 2 matrix. So EA minus lambda times EB minus lambda. So EA minus lambda times EB minus lambda. And then we get minus h squared. So now let's multiply through, and we get that 0 has to be equal to EA, EB. Then we have two terms that are going to be multiplied by minus lambda, which are EA and EB. So we can write this as minus lambda factor of EA plus EB. And then we have plus lambda squared minus h bar squared. So you can see this is simply a quadratic formula. So we can find each of the eigenvalues for lambda by, just solving this. And what are the interpretation of the eigenvalues? That's simply the energy. So we will have two different energies. One will be E plus and one we can call E minus, because the difference between the two will be the minus sign in front. But actually, you can actually put all together, I guess, into E plus minus. Okay, so by using the quadratic formula, we get that this is 1/2 of, and why 1/2? Actually, maybe let's not get ahead of myself. So this is minus B. B is EA plus EB with a minus sign, so we get EA plus EB. Then we get plus or minus B squared, which is EA plus EB squared, minus 4 times C times A. So A is 1 and C is EA, EB, and then minus h squared. And all of this is divided by 2a. But a is 1, so times 1/2. So now we can simplify this square root a little bit. So e plus minus will be the same thing at the start. So EA plus EB. And then inside the square root, we get EA squared plus 2EA EB. And let me write this right next to this part. So minus 4EA EB plus EB squared plus 4h squared. So now we can write this as follows. So 1/2 of EA plus EB plus or minus, and now we get this 2AEB cancels out partially with this one, so we get minus 2AEB. So that means that this is basically EA minus EB squared, but then of course with the additional 4h squared. There we go. So this is our result from part 1, right? These are the exact energy levels. So what about part 2, right? This time we want to do it using perturbation theory. So in second order perturbation theory, what we need to do is just take our 0th order, right? Which in this case, we have EA0, for example, and EB0, which of course are simply EA and EB. And we want to find the first and second order corrections, but the first aren't really, that's why they don't ask us to find them, because the first order correction terms, those are, because it's non-degenerate, it's simply the expectation value of H prime in each state. So basically, it is psi A, H prime, psi A, which is 0, and that is of course the same as psi B, H prime, psi B. So the first order corrections are both 0. That's why they don't ask us to find them. Now, what about the second order ones, right? EA2. Now, by using the formula for this, it is psi B, H prime, psi A squared divided by EA minus EB. Now this, again, by definition, we can see it here on the left-hand side. This is simply H squared divided by EA minus EB. And then EB2, right, the second order correction for EB will be the exact same thing, actually. So psi A, H prime, psi B squared, or almost the same, of course, EB minus EA. And this time, this thing is, well, it's also H squared, but in the denominator, we have EB minus EA. So the energy, right, I don't know, let's call them 1 and 2. So E1 and 2 are going to be EA plus this correction, which is so plus H squared EA minus EB, and then plus the other correction, so H squared EB minus EA. So these are our results. So now let's go to part C. Estimate the ground state energy of the perturbed system using the variational principle with a trial function of the form psi is cosine phi psi A plus sine phi psi B, with phi an adjustable parameter. So let's do that. So variational principle, just a reminder, what does it mean? It means that if we take the expectation value of our of our system in general, and if we take this expectation value with respect to a trial function, then this will always overestimate the ground state energy of the system. So we like to introduce a variational parameter, which we can then derive with respect to it and find the smallest possible energy. Okay, so let's do that. And what is our psi? Well, that's given to us. We know that it is cosine phi psi A plus sine phi psi B. Now let me double check. Yes, cosine psi A, yes. Now this is already normalized, right? If you take the integral of this, the inner product, you get 1 is equal to cosine squared phi plus sine squared phi, and the inner product is going to be 1 because psi A and psi B are normalized themselves. And phi here is simply a parameter. It doesn't have anything to do with the angle in spherical coordinates. It's simply a parameter. That's why you can take it out of the integral. And that's why this is 1. Otherwise, it wouldn't be 1. Okay. So with that out of the way, let's take this formula and plug in our psi and our h. So we know that the bra is bra of cosine phi psi A plus sine phi psi B. And then we have h, which I will write with a different color, which is h0 plus h prime And then we have the same thing. So cosine phi psi A plus sine of phi psi B. So we want to find what this is, right? This is the expectation value of the Hamiltonian. So now we have to multiply it through. So let's do that. So we get cosine phi psi A times H0 times cosine phi of psi A. So since phi is a constant, we can take the cosine outside. So we get cosine squared of phi. And then we get psi A H0 psi A, which we know is EA. Okay, so now let's do the same, but for a different one. So let me actually change. Can I change the color of this pen? Oh, I can. That's nice. Nice. Now let's go for cosine times H0 times this one, sine phi. So when we do that, we get sine phi cosine phi, the order doesn't matter there, times psi A H0 psi B. But this is 0, right? By definition, we don't have off-diagonal terms for the unperturbed system. So this entire thing is 0. And that's actually going to happen quite often, because the next term is sine. Well, it depends which one you want to multiply. Maybe we can continue with cosine, with the cosine. So then we go for this times this. And now once again, what do we have? We have cosine squared. I'm going to make this a little bit less thick. There we go. So cosine squared of phi times psi A H prime psi A. But by definition, again, right here, this is 0. So this thing goes bye-bye. So the part that will not be 0 here will be when from cosine we multiply with H prime and then with this part, because then we will get sine of phi cosine phi times psi A H prime psi B, and this is H. Okay, so now let's do the same, but multiplying with the sine. So now when sine, so plus, now sine multiplies H0 and then this part. But when we do that, we get bra of psi B, H0 ket of psi A, and that is by definition 0. So the next term is sine, or this sine times H0 times this. So when we do that, we get sine squared of phi psi B H0 psi B, and this is simply EB. Now the next one is sine times H prime times cosine. So we get plus, and here what do we have? We have sine of phi cosine phi times psi B H prime and psi A. So in this case, this thing here is simply H. Yeah. And there's two terms that I haven't multiplied yet, which is, I believe, sine times the H0 part. So basically this times this, which is 0. Sorry, that's the one we already did, actually. So the one this one here is 0, and the other one is this times this one, which is also 0. So all that we are left with is this. And the reason, once again, is because we are simply using the definitions, right? This is what they told us that the Hamiltonian looks like. So now let's write this down, but a little bit cleaner. So we get EA times cosine squared of phi plus, and now notice we have sine phi cosine phi times H, sine phi cosine phi times H. So this is simply sine of phi cosine phi times 2H. And then finally, we have this part, which is EB sine squared of phi. And this entire thing, of course, is the expectation value of the Hamiltonian. Okay, so now we want to find the smallest possible value for this energy, right? Which value for phi makes this energy as small as possible so that we can get as close as possible to the ground state energy as we can. So let's take the derivative of the expectation value of h with respect to our variational parameter phi. So let's take each one of these derivatives. So we get from the first one 2EA cosine phi, and now because of the chain rule, times the derivative of cosine, which is minus sine. And then we have this term where we get plus 2h times sine of phi, its derivative, which is cosine, times cosine. So we get cosine squared of phi. And then we get plus and now sine times the derivative of cosine, which is minus sine. So this is actually minus. So we get, maybe let's factor out 2h, and we get minus sine squared of phi. And then finally we have this part. So we get plus 2EB. Actually, the b is smaller, I guess. And then sine times the derivative of sine, which is cosine. Okay, so there we go. Now, what do we have? Well, notice, and this of course has to be equal to 0, by the way. And notice that we have quite a few things we can factor together. So we have 2 cosine phi sine phi and 2 sine phi cosine phi, which is the same. So we can now use an incredibly important trigonometric identity that you must know, that 2 sine phi cosine phi, this is sine of 2 phi, and that cosine squared of phi minus sine squared of phi, this is cosine of 2 phi. These trigonometric identities you must know. Okay, so by using that, we can factor this and this together. So we get 2 times, and then what do we have? We have, this would be sine. Actually, the 2's go into the expression, so actually we don't have the 2's. So we have sine of 2 phi times EB minus EA. And then we have this term right here, which is plus 2h, and then we have cosine of 2 phi. So now we have a trigonometric equation. So we can solve this either by finding the tangent or the cotangent. I would rather work with the tangent than the cotangent. So let's put this to one side. So we have that sine of 2 phi, this is equal to minus 2h cosine of 2 phi, and now divided by EB minus EA. And now we can divide this by cosine so that we get everything that depends on phi on one side, cosine of 2 phi. And this, of course, is tangent of 2 phi. Just to be clear. And well, let me write this in the center. So this is minus 2h. So now we have an expression for the tangent of 2 phi, but keep in mind that our objective is to find an expression either for phi or for cosine phi or sine phi that we can then plug in here. That is the objective. And at the moment, there is no tangent here, and maybe we can turn everything into tangent somehow, but that doesn't really seem to be particularly easy. So we need to find some expression or some way to transform this equation into equations that give us sine of phi is equal to something and cosine phi is equal to something. And that we can then plug in. But at the moment, we don't have that. So for that reason, we will have to use some trigonometric identities to get to that point. And since we're going to be doing some algebra, and this here is simply a constant, we can simply rename it as minus epsilon, with epsilon 2h divided by EB minus EA. We will leave the minus sign outside. Okay, so how could we do this? Well, we have sine and cosine, and we know how to write cosine in terms of sine because of another incredibly important trigonometric identity that you must know, right? Sine squared of 2 phi plus cosine squared of 2 phi. So from this, we can see that cosine of 2 phi is the square root of 1 minus sine squared of 2 phi. So we can plug this in here, and we get that sine of 2 phi divided by the square root of 1 minus sine squared of 2 phi. This is minus epsilon. But now we can square this thing, and we can multiply the denominator. So we get sine squared times 2 phi. This is equal to minus epsilon squared, which is epsilon squared, times 1 minus sine squared of 2 phi. Now we can put all the sine squares together to the left-hand side. So we get sine squared of 2 phi times 1 plus epsilon squared, right? Epsilon squared, of course, coming from this term. And this is equal to epsilon squared. So now we can solve for sine squared. So sine squared of 2 phi is epsilon squared divided by 1 plus epsilon squared. Okay, the issue, however, at least for now, is that there is a sine squared, but it is of phi, not of 2 phi. So how could we possibly get to that point, right? How can we transform it? Because we got to this point, but it isn't really what we want. Well, there is something that we could use, because we know that cosine of an angle, right? If we have cosine squared of phi, this is 1/2 of minus, in this case it's plus actually, so plus cosine of 2 phi. 1/2 times 1, sorry, there we go. Another incredibly important trigonometric identity that you must know. And similarly for sine squared of phi, this is 1/2, 1 minus sine of 2 phi. So if we find, sorry, this is not, this is cosine, sorry, it's minus cosine. So if we find cosine of 2 phi, we can then plug it in and find both cosine squared and sine squared, which would be very, very good. So that way we could find cosine squared and sine squared to plug in here. But we still have this term right here, which we can rewrite as h times sine of 2 phi, which is precisely what we have here if we take the square root. Sorry, not there, here, if we take the square root. So let's do it, and we will see that sine of 2 phi, well, this is plus or minus, right, epsilon divided by 1 plus epsilon squared inside of our square root. So this is sine of 2 phi, which is already a very important result. And now, what is the easiest way of finding cosine of 2 phi? Well, it is by going back to this here, right? Because we know what sine squared is, so cosine of 2 phi we can find from this very equation. So we can just take square root of, or actually maybe let's write it like this, because we have to be very careful with the signs. So cosine squared of 2 phi, this is 1 minus sine squared of 2 phi, which is epsilon squared, 1 plus epsilon squared. So minus epsilon squared divided by 1 plus epsilon squared. So we can take minimum common denominator here. So we get 1 plus epsilon squared minus epsilon squared divided by 1 plus epsilon squared, which is simply 1 over 1 plus epsilon squared. And now we can take the square root of this. So we get cosine of 2 phi. This is plus or minus 1 over 1 plus epsilon squared. Now the question is it plus or minus? Is it minus or plus? Usually it doesn't matter. But this time there is a constraint that we must remember. This isn't completely free. This comes from this here. So we need sine divided by cosine to be minus epsilon. So let's do a quick test. If we choose it to be plus or minus, what do we get? So we know that we need sine of 2 phi over cosine of 2 phi to be equal to minus epsilon. So what is sine? We know that it is epsilon squared. Oh, actually the square root, right? So it is plus or minus epsilon divided by square root of 1 plus epsilon squared. And from what we're seeing here, I need a square root here, by the way. And what about cosine of 2 phi? Well, cosine of 2 phi, we would have 1 divided by square root of 1 plus epsilon squared. And then something in front, right? Either plus or minus or plus. So if we do this, this cancels out with this, and we end up with plus or minus epsilon. And then we also are dividing by something times 1, right? Maybe plus or minus, maybe minus or plus. But we need to get minus epsilon. So if we choose cosine as plus or minus, we end up with plus minus. So we get plus epsilon in both cases. It is impossible to get minus epsilon if we choose cosine phi as plus minus. We need to take it as minus plus, so as minus plus, because that way, if we are dealing with the uppercase, it will be minus, and if we are dealing with the minus case, it will be minus as well, which is what we need. So for that reason, cosine is minus plus, not plus minus, because it needs to be consistent with what is going on with sine, because they are connected. You cannot simply take them as independent cases because they are not independent. Okay, so now we have every value that we need. We have sine of 2 phi, cosine 2 phi. Now we only need to plug them in here. So we can find cosine squared and sine squared and plug them into our Hamiltonian. So for cosine squared, this is 1/2 1 plus cosine of 2 phi. So that is minus or plus 1 over square root of 1 plus epsilon squared. And for sine squared, this is 1/2 1 minus, and since we are dealing with this time it is plus minus. Oh no, actually no, because this is cosine, never mind, so it's the same. So it is minus minus plus, so it is plus minus epsilon divided by 1 plus epsilon squared. Wait, no, this is incorrect. And here, cosine of 2 phi, this is the same, but this time the minus plus has a minus in front, so we end up with plus minus 1 over 1 plus epsilon squared. So now we can plug all of this back into our Hamiltonian. So I will rewrite it down here. So the expectation value of the Hamiltonian used to be EA times, I think it was cosine squared. Let me double check. Yeah, EA times cosine squared. Now cosine squared is this thing. So it is EA times 1/2. Actually, let me put the 1/2 here. So EA over 2, 1 minus plus 1 over this thing. And then next we have 2h, h sine of 2 phi. So h sine of 2 phi. Sine of 2 phi is this. So plus h, actually plus or minus, right? Plus or minus h times epsilon divided by 1 plus epsilon squared. And finally, we have plus EB times the sine squared. So we get EB over 2 And then 1 plus or minus 1 over 1 plus epsilon squared. Okay. Now let's try to simplify this. So let's see, we have EA, so we have 1/2 multiplying a lot of things, not everything, but we could try and factor it out. So 1/2, and then we have EA plus EB. Okay, so we used this and this, and then we have this plus, so we have a lot of things with this 1 plus epsilon squared, blah, blah, blah. So let's try to put all of that together. So we could go for plus minus, and then the one with minus plus will have a minus in front. So plus or minus 2 times h bar, then the curse of the physicist, h epsilon, the 2 of course because of the 1/2 in front, right? Because we factored it out, and they didn't have a 1/2 before. Then we have to add this, so plus EB, the plus or minus is in front of all of this. And then we have minus EA. Is this correct? Yeah, minus EA. And all of this divided by 1 plus epsilon squared. All right. What else can we do to this? Now what we could try is to take this and expand it by using the binomial theorem, because epsilon is very, very small. Let's go back to its definition. It is of the order of the perturbation divided by the energies of the unperturbed system, which are by definition much, much greater, so epsilon is very small. So for that reason, we can expand 1 plus epsilon squared in a square root, just as we did in the previous videos, right? Using the binomial theorem, which, in case you don't recall, this, at least for this sort of case, so 1 plus x, and this is to the minus n, this would be 1, and then minus n times x, divided by 1 factorial, and then you get like plus n, I think, times n plus 1. But this is x squared. It is something like this, but it is of the order x squared. And since we are already dealing with epsilon squared, x squared would be epsilon to the 4th, which is already way too small, and it doesn't matter. So for our purposes, this is good enough. Okay, so now let's do that. So we get 1 minus, and what is n? N is 1/2. Well, it is minus 1/2, the exponent, but in this case, n is 1/2, right? The minus is already in front. So minus 1/2 times epsilon squared. So this is what we get. It is basically the same. It is a very good approximation. So we can plug this in here. So we get 1/2 of, okay, what sort of a parenthesis is that? 1/2 of EA plus EB, plus or minus, and what do we have then? Then we have 2h epsilon plus EB minus EA times, and this is 1 minus epsilon squared over 2. And we can also plug in the value for epsilon, right? So epsilon, as we had just seen, epsilon is simply, I think it is 2h divided by EB minus EA. I'm going to double check. Epsilon, it is 2h EB minus EA, yes. So let me write it as such. So this is, well, there's 4h squared divided by EB minus EA squared, and there's a 1/2 here. And we have an epsilon here as well, so we get 2h squared here as well. So we get 4h squared, and then divided by EB minus EA. So let's now multiply through. Now the first part, of course, there is no change. Now what do we have in this plus or minus part? We get, let's see, 4h squared. This is times 1, so like no change. So 4h squared epsilon EB, sorry, minus EA. But then we get something of the order of h to the 4th power, which is so small, right? H is already very small. We are in perturbation theory, so h is super small. So to the 4th power, you can't even notice. Then we have EB minus EA times that or other thing. So first times 1, so you get plus EB minus EA. And then times this part, right? So this entire thing, I mean. So we get minus 4h squared, and then divided by 2 EB minus EA. All right. So of course there's going to be a little simplification here. This will go to 2. And now notice we have 4h squared EB minus EA minus 2h squared. So this thing right here would be at 2. So 2h squared, this goes away. And we are left with this. So now we have 2 cases that we have to consider. So E plus, in which case we get 1/2 and the plus sign. So we get EA plus EB plus 2h squared EB minus EA, and then plus EB minus EA. So the EAs cancel out, and we get 2 EB. And we can now multiply by 1/2. So the first result is EB plus h squared divided by EB minus EA. And in the second case, E minus, we get something very similar, right? But this time, let's see. So we get EA plus EA. So the EAs are the ones that don't cancel out, and the EBs cancel out. And the other difference is that now we have minus h squared EB minus EA. So these are our results when using the variational principle. So this is equal to E plus. Okay. Right, so part D, what they want from us now is to compare your answers to A, B, and C, and see, how accurate the variational principle is. So the issue is that our result in part C has this very neat form, but in part A, we have this nasty square root. So now to compare them, we need to expand the square root and try to get an approximate expression, and it will be a relatively good one because h is very small, right? In perturbation theory, the perturbation parameter is very small, and we want to do that to be able to compare the expressions. Otherwise, not really too much we can do to compare them. So let's expand this square root. So to expand them, we need to get it to a form like 1 plus x to the n power, right? And how can we do that here? Well, let's factor out, because the x has to be very small, the only way to do it is to factor out EA minus EB, which, by the way, we can rewrite as EB minus EA just for consistency, because that's the way it appears everywhere else. It doesn't really matter much, but in our other results right here, it is always EB minus EA, so it's going to be useful. Okay, so now this square root is going to be factoring out EB minus EA. It is this times the square root of 1 plus 4h squared divided by EB minus EA squared. Now, using the binomial theorem, we can expand this. So EB minus EA remains the same, of course, but then we have 1 plus 1/2 times this. So the 4 will become 2, so 2h squared EB minus EA. So, and of course, any higher order terms will be 0 because we are going to be like, for example, x squared, which is the next term, will have h to the 4th power, which is so big that it will not make any noticeable difference, right? This is an approximation. So let's plug it in here. And we get, I'm going to multiply it right away. So EB minus EA plus 2h squared EB minus EA. Not squared anymore because of the product. Wait, what was that? Okay. So now let's go for each one of these cases. So for example, E plus will be 1/2 of EA plus EB plus EB minus EA plus 2h squared EB minus EA. So here the EA's cancel out and the EB's add up. So we get 2EB, but 1/2 of it will be simply EB, and then plus h squared EB minus EA. And similarly, for the negative case, sorry, this is supposed to be E plus, by the way, not EA. And for the negative case, or the minus sign, this time it will be the EBs that cancel out, right? Here and here, and the EAs add up. So we get EA minus, right? This sign is changed by this minus, h squared EB minus EA. So these are our results, our exact results using, of course, this approximation. And we can see that it's precisely the same that we got in part C. EB plus h squared, blah, 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 exactly the same. So what about the results from part B? Well, in part B, what we got is this thing. But we can see E2 is the same as our E plus, right? E plus and E2 are the same, but E1 in this case isn't the same. There's this minus sign. But the reason for that is that we wrote this as EA minus EB. So we can simply factor out a minus sign. So minus, and we get the EB minus EA. So it's indeed the same. So we can see that we got the exact states by using the variational principle. And that is, of course, because of the fact that this wave function that we used is a linear combination of sines and cosines, and we know that a linear combination of those forms a complete space. So of course, these can indeed form the actual wave functions of the state. And that is why the variational principle was so accurate. So that was this problem. It was a bit long maybe, but not particularly difficult. We used basically every technique that we have seen so far in perturbation theory. We found the exact eigenvalues and then the different techniques and a lot of binomial theorem. But the ideas behind it are not particularly hard, but the hardest is, finding how to set up the problem by using the matrix notations. Once you get the hang of that, it isn't the worst thing in the world. So I hope this was useful to you. If it was, please make sure to subscribe to the channel, leave a like, a comment. It doesn't cost you anything, but it really helps me out a lot. And maybe let your classmates know about this. Might be helpful for them as well. So I'll see you in the next video. Thank you very much for watching.